Thank you for the introduction. So my name is Shuyue Wang. I'm from KTH, Sweden. Today, I'm going to present our work, numerical modeling of tactile fracture involving two length scales. So the first question is like, why are we using two length scales? Imagine we have a continuum body, and there is like a void embedded. When we load it in tension, the void will start to grow, and then they will link up together, leading to fracture. We call it flat dimple rupture in the opening mode. And instead of loading it in tension, we can also load it in shear. What happens with the void, it will get elongated and rotating, and finally link up together, leading to shear dimple rupture in shear mode. And as you can see in the picture here, that these two lengths is different. They are different size. And we call the first one hydrostatic length and the second one shear length. And as you can see in the picture, the shear length should be smaller than the hydrostatic length. Based on these observations, we try to answer the questions about how should these hydrostatic and shear lengths be implemented in the model. We try to answer is the separation of length scales necessary to capture transition from flat to shear dimple rupture, for instance, cap cone failure. And if it's necessary for accurate prediction of critical loads of tactile fracture for a wide range of stress reactivity and deviatoric stress state. What we do is we use a porous plasticity model, GTO model. And for the state variable, we have a flow stress in the matrix. We have also void volume fraction determining the damage parameter. In the yield surface, if there's no void evolution, then we will have a Mises surface. And if there's any void, we will have a GTM surface. Imagine now we have load acting on the body. So the plastic special rate of gradient acting on the yield surface can be decomposed into a hydrostatic contribution related to the flat dimple rupture associated with a longer hydrostatic length and a deviatoric contribution related to the shear length. With that in mind, we can describe the evolution of void volume fraction, including void growth, shear modification, and nucleation. From those parameters, we can identify the ones which is connected to hydrostatic contribution and shear contribution. And therefore, we can sum them as a shear mode of failure, all these parameters over there, and the opening mode of failure. So the total void volume evolution will be the sum of the hydrostatic one plus the shear one. However, as you can see in the literature, the local GTN model gives rise to strain localization, and the result will become mesh dependent. Therefore, we used a non-local integral approach to tackle this problem. This is then a method where you evaluate the void volume fraction and counter the non-local contribution, which is a weighted average of a region of influence characterized by the length. And in this case, we will do this for both the shear contribution and the hydrostatic contribution. So finally, the evolution of damage is a non-local contribution of the hydrostatic and the shear void volume growth. With that in mind, we started with a numerical study of how this model works and how this parameter behaves. The material we looked at was an elastic plastic material. As I mentioned, we are accounting for void growth, nucleation, and shear enhancement together with these two lengths. In this study, we focus on the shear contribution. So we are looking for this shear parameter, Ks. Some literature call it K omega. And we are looking at what happens if we vary this shear length, which should be shorter than the hydrostatic length according to experimental observations. The test geometry we looked at includes axisymmetric uniaxial tension tests and a single edge notch bend specimens. These two will start, the crack in these two specimens will start to growing as an opening mode and finally shears off. We also looked at the notch tube specimen and the modified isopesco specimen, where these two will be loaded in simple shear. But the notch tube one will have a more homogeneous plastic gradient, and this modified isopesco specimen can have different strong rate of plastic gradient in the region by changing the dimensions. So if we look at the numerical result, first we try to look at the flat to shear failure. So if we have the shear length scale equal to the hydrostatic length scale, basically we have only one length scale as in the literature, then no matter how fine mesh we have, we will never be able to capture this cap-cone failure. However, if we have a smaller shear length, basically we're using two different length scales interpreting on these two different mechanisms, then we can find with a good mesh refinement, we can find this cap-cone failure as you saw in the picture here. And if we look at the penetration of the free surface, you can also see that at the beginning, when the specimen is opening up, it's mainly determined by the hydrostatic length. No matter how much we change the shear length, it will not affect the width of the crack. However, in the transition region, you can see there, it really depends on the shear length. If we look at the shear mode of failure, you can see that the specimen with homogeneous plastic gradients, it will mainly be dependent on the shear parameter KLS. And the isopesco specimen with more stronger gradient will be dependent on both KS and the shear length. And the fracture mode in these two cases will not be dependent on these parameters. So now we understand how this parameter works on the model. We try to apply it in real materials. What we did is investigation of pressure riser steel. We looked at, first we extracted the material matrix, which follows a Vos-Harding rule. And from there, we also deducted some 3-point bend specimen with both deep and shallow crack. From this specimen, we can extract both force CMOD curve, but we can also find this JR curve. And from all those results, we can extract these fracture parameters, such as initial void volume fraction, coalescence, final failure, and also nucleation parameters. So the next step is look at how this model behaves in shear. We did several tests with isopesco specimens with different dimensions in this critical region. However, we found in both materials that the model, the simulation model, overshoots this than the experiment prediction. The question arises, why do we have this behavior? One assumption we made in this model is that we have a vomesis material, and it will harden as isotropic hardening low. So finally, the yield surface should look like this, like a homogeneous circle. And then we should have a uniaxial tension test at that point. And the simple shear should follow in that point. But according to the experiment, the experiment had a smaller, like weaker hardening behavior. One explanation can be found, instead of following an isotropic hardening all the way, it becomes a Tresca's yield surface in the end. And this phenomenon is called the distortional hardening in the literature. Another theory we have, if we look at the microscopic cone structures of the material, after large deformation, you can see how the cone structure gets really deformed and allocated. And what happens here is instead of a yield surface growing isotropically, we had an anisotropic growing of the yield surface that, for instance, can lead up to Hill's yield surface. And here we will also have this good prediction of uniaxial tension test, but too strong prediction in the simulation compared to the experiment. And this phenomenon is called the textural evolution in the literature. So that's what we've done so far. I will try to summarize our work right now. So we found that flat dimple rupture is primarily associated with the hydrostatic length, and the shear failure is associated with the deviatoric parameter Ls, the shear length, and controlled by the shear parameter Ks. We need to separate these two length scales in order to capture these flat to shear fracture modes. And calibration of these shear parameters is quite inclusive, and we believe there's something to do with nucleation, because in that field, it's still a question mark. We haven't found everything yet. And from the calibration, we can find something called distortional hardening, where von Mises yield surface grows into a Tresca's surface, or something called textural evolution, leading to the material soften or harden at finite deformation. So these are the two questions we are working on to implement in our model. And we have one publication that is about the numerical study. And that's everything for me. Thank you for your attention.